What exactly is cell degradation? What is cell aging? And how can you learn this from a piece of cake? Find that out in Hyfindr Tech Talks with DILICO in just a minute. So what could cause this? What could cause this starvation? This gets like a hamburger, it just gets sandwiched in between the cells.
800,000. Yeah, 800,000 euro more incomes.
I think it's the most edible explanation anyone can get. Welcome to Hyfindr Tech Talks. My name is Steven. Today we're talking about degradation of cells in electrolysers, and for that I have an expert here, someone who's worked in this area for quite some time. He founded a company around that about 10 years ago that is solely involved in measuring the insides of the cells and everything around that. He has a PhD in engineering, and I'm very pleased to welcome Maik Heuer from DILICO Engineering.
Hello, Steven. Nice
Hello,
to meet
Maik.
you.
Great to have you here.
Yeah.
Maik, so what did you bring with you today? Are these cells or what are they?
No, we have here our measurement tool to look into the cell,
Okay.
to visualize aging or degradation. And this is our interesting tool for the electrolyzer industry.
For the electrolyzer. Okay, so we'll talk about this in detail in a bit.
Yeah.
But first I want to ask you, Maik, what exactly is cell degradation?
Yeah, degradation is the changing of the performance of the cell components, and overall also when you have an electrolyzer cell, in the reduction of the hydrogen production.
Okay,
Yeah.
so it is basically the cell getting less performant. Is it the same thing like aging?
Yeah, it's nearly the same aging, degradation. Degradation, you can describe the process,
Yes.
and finally you can measure then the aging effects of
Okay,
it.
so
Yeah.
okay. And you say there are various effects of aging.
Yes. Yeah, different effects. Corrosion, for example, on the electrode. When you have the sealings, for example, but everything is closed, gas closed.
Okay,
then
so I have a bit of a diagram here
Yeah.
for that. So you mentioned the one side, the ceilings could be affected. Yes.
Yes, we have here the main parts of, of an electrolyzer cell: the membrane, the bipolar plate, sealing, and the electrode. Yeah.
Okay.
And I showed here the different degradation effects of each cell component. And one example is related to our crumb cheese.
Ah, crumb cake. Okay,
Our crumb cake.
Get that right in. So yes, so this we can imagine is a cell, right?
Yes, this could be the surface of an electrode, the anode side of an electrolyzer where oxygen is produced. And the crumbs could be then the catalyst. And the catalysts, iridium or ruthenium, there happens the reaction.
Okay.
That means water and electricity at this point producing then hydrogen.
So essentially, this is sitting in this is one of the cells that's being stacked in an electrolyzer, and on this side you would have a fluid. So you would have water.
Yeah.
And this water, and then we have electricity put on there, and then essentially this is the cell that will kind of initiate the separation. And this would be like as if you're looking through an electron microscope. You would see the catalysts like this. These are the crumbs.
Yeah.
Right.
And on the anode side, we have high voltage differences, and we have the oxygen production. And due to side reactions, we have also the production of oxygen radicals.
Okay.
And these radicals will lay down on the surface of these crumbs,
All right.
on the catalyst. And then it could happen after a certain time that these radicals blocking the catalyst surface, and then I cannot produce in that good way hydrogen.
Okay, so as we see here, they're covered with them, so that is obviously inhibiting their performance. Okay, so thank you for this very visual explanation of aging. I think it's the most edible explanation anyone can get.
Yes.
Right. Okay, but other than that, there are more effects.
Yes, I have here an example from my time at the university. You can see here membrane, and you can see what happens when you have a lot of stress.
So this black part is the membrane?
This is the membrane.
So here we have the top view, and we have the same thing from the side view.
Yes.
All right. Okay.
And you can see what happens under really, really bad conditions, that you have thermal hotspots. And then we have a hole inside the membrane, and then the reaction will not anymore work.
Okay, obviously.
And this you must avoid.
And it's dangerous, isn't it? Then you can have permeation of the gas or movement of the gas.
And normally you have some safety chain in your system. So when you close to this situation, normally you will detect it previously that you not have this situation in real.
All right. Okay.
But this is only an example to show the interesting people what could happen.
What could happen? Okay.
And here it's also an effect you can see when the ceilings are damaged during operation. Yeah.
So this is where we had a round cell here, and these are seals that basically hold it in place.
And this ceiling has abrasion, and this leads then to this effect that we have a leakage. And
so we have a leakage through here.
And due to the leakage, we have a hot spot, and then we have here thermal damage of the cell.
All right. Okay. So also performance going down. Okay.
And finally, you can see it here when you want to measure the situation of your cell. Is here the voltage over the current.
Yes.
And you can see here when you have a new membrane electrode assembly. You have here the voltage over the current. It's a good situation. And due to the degradation effects, the voltage go down. This is for a fuel cell, for example.
So this is the famous UI diagram of any cell. So we're talking electrolyzer, but this could also be a fuel cell, any kind of cell system. And then, so this is, as you increase the current, the voltage goes down, basically.
For the fuel cell.
For the fuel cell.
In electrolyzer mode's a little bit different.
Okay.
But generally, the surface here below shows then the maximum power that the cell produced, and you can see here this part is bigger than here, or the distance, and so a new membrane has more electricity produced compared to an old membrane. For fuel cell, for example.
Okay, so I mean, this is one way of measuring the performance. So what is now your additional way of measuring this?
Our way is to measure inside the cell.
Okay.
That means we bring a sensor system into the cell to visualize the performance of the cell over the membrane surface.
So this is where, and I'll take this away briefly. So this is where these come in.
Yes.
Right. Okay. So can you explain this? What this is?
This is our DILICO CURR TEMP sensor layer.
Yes.
We designed it for a real system. It's for electrolyzer system.
So that means that this is, you put this into the electrolyzer. This gets like a hamburger. It just gets sandwiched in between the cells, basically. Okay.
Like a sandwich.
Yes.
And we have here several of the segments, and in each of the segments we have integrated a temperature and a current sensor, and then we can measure at each of the segments the current and the temperature. When you have this information of the completely area here, where we have, I think, 256 segments here, then you know exactly what happens at this area and at this area of your cell. And then you have a better view inside the cell, and you can say, okay, in the entrance maybe the conditions are bad, you must change something, and in the middle you have good performance, and then you can use this information to react by changing your operating parameters, for example, or you can compare different materials.
Okay. And what difference does that make for the owners of such systems?
When you know what happens inside your cell, you can then change different parameters to increase, for example, the efficiency of your cell. I have also an example here on the slide. When you have a 1 megawatt electrolyzer and you can improve the efficiency up to 1%, and then you can generate more than 160 tons more of hydrogen over a lifetime of 80,000 hours here expected. And this is a lot, and especially a lot of money that you can make when you sell then the additional production of hydrogen.
So 160 tons, that's over a lifetime. So that means 1% more can already give you that. That's, if you take, price of hydrogen goes up and down. If you take €5, what do we say? It's like 800,000.
800,000 euro more incomes.
Yes,
this is then a reason to invest also in measurement technology to improve your cells from the beginning of research activities, but also when you run your system by the end user. When you monitor it, then you get information and you can use this.
Before you show us this equipment and how you do that more in detail, just wanted to ask, what factors actually influence this degradation or this aging?
There are several effects that leads to aging inside the cell. As we talked before, the corrosion at the electrode. You have also on the membrane mechanical stress.
Because so moving around.
The inlet pressure goes up to 50 bar. So on the oxygen side you have ambient pressure. On the hydrogen side you have up to 50 bar. So you have a lot of pressure difference. So you have mechanical stress. Then the electrolyzer runs 80-90 degree. You have high voltage differences, and this is not the best condition to run the system for 40 or 80,000 hours. And this makes something with the components. And this leads to this that the hydrogen production goes down over the time.
So, like for example, fluctuation of currents or so, would that be an effect?
Start-stop could have an effect. I have an example from a partner from us in the fuel cell area, for example. They have normal operations starting the cell, but they can't see any problems. And with our tool, with this sensor layer here that they have integrated, they saw that they have, especially in the startup phase, they have starvation. That means in this fuel cell application, it was not enough hydrogen at each point of the membrane. And this has a high aging effect.
Maybe we can actually have a look at that, because we have it on the chart here, but you also brought it in real. So what do we have here? This is like the big one. This is something which you would sandwich into the...
this is a small one for electrolyzer.
Electrolysers, for a round cell.
For a round cell.
Just out of curiosity, do we see a lot of round cells?
In the electrolyzer area, yes. They are more round. In the fuel cell area, it's more quadratic.
Why is that?
Maybe due to the high pressure. It could be a reason, because when you are round, you have a better force distribution for clamping. This could be a reason, but it could be also a reason for the flow performance of the fluids.
So this is not afraid of the fluids. This can touch.
We have no contact to the fluids. We are normally behind the bipolar plate. And the advantage is that then the system can run longer than a normal cell.
So this will be
the first units we installed are from 2008, and they're still in operation.
So this basically has all the data coming through from the sensors, goes into this. And what is this?
This is our data acquisition system. All the data goes inside, and then we convert it. And we have here our digital report. You need only USB port at your PC, and then you receive the data. And then, you know what happens inside your cell.
Inside your system, And what does it take to set it up?
Nothing. You don't need calibration or so. So you can start instantly installing the software and then running.
Here we also have another photo of how you sandwiched it.
Here we have integrated in the stack 3 units of this DILICO CURR TEMP version on the first cell, in the middle, and on the last cell. And then you have also a good information not only on one cell, also over the length.
This one seems a bit different. So here you have basically this box at every cell. Sometimes it depends also on the space that we have around the cell. Some customers put it in a box, and then it's difficult to add our data acquisition system. Then we must bring the electronic directly on the plate. So just to understand, this is where would you typically see this? Would you see this in running systems? So like an electrolyzer system that's running somewhere on the field for many years, or is this more like a lab, like a development setup?
Normally it's used really in the research area for developing new cells. But from my opinion, it's also good to integrate it in some of your customers' power plant. Because then you get a lot of information on the field, not in the lab.
So then you see how it's actually running. I think you also brought some examples of how we see those results. Let's see. There you go.
Here you can see a measurement. It's from my PhD.
Okay.
This is here a standard current density profile during operation in a fuel cell, and here you can see that we have a difference, on the entrance here.
So just to, sorry to interrupt you, but just to understand this thing, what are we looking at? So we have, it will be this kind of setup here, and we're getting data from each of the fields, and this is being automatically plotted on the chart. And what it's showing here? What is it showing here?
You can see here this structure here. This is one segment, second, third segment, and so on. Like here.
The structure at the bottom of the diagram. These.
No. I mean here the segments of this curve.
On the curve. All right.
And each of the segments shows the current amount, the current production. And what we here have done is, you can see the time is increasing. Is warm up the cell doing the operation from 20 degree to 70 degree. And you can see that we have on the entrance lower current production, in the middle of this membrane more current production, and the outlet it goes down.
Okay, so that means essentially what we will be seeing here is that on this side there's less current production, and then here in the middle there's much more. And here there's less. This is what this is telling us. Okay. So what do I want? Do I want it evenly, or is that a good thing to have it in this way?
You can compare it maybe with a car. You have 4 tires. And when you only run on 3 tires, then the tire number 4 is not working and it's in a good condition. And the other 3 tires are working more hard because they have the same power to bring on the street, and then they have more aging effects. So we have here maybe more aging effects than here. And the target is to make it flat.
So as flat as possible.
Everything is in a good way. Here you can see starvation now. You can see very big disturbances. And that means that we have...
This is again over time. So we see this is one time, this is the next time, next time, and then we see,
now it's
so we had a low production here and high production here. Because for whatever reason this place isn't as well supplied as this side. And then at some point we just have low supply there.
So we have nearly no current production because no oxygen or air came to the reaction zone at this
So
example.
What could cause this? What could cause this starvation?
Here, for example, it's the bad flow field design of the bipolar plate. You bring, for example, in a fuel cell, the gases into the cell, on the cathode side, the air. And when the flow field has not a good design, then you have bad streaming conditions or flowing conditions. And then it happens that the oxygen goes not through the membrane where the reaction happens. And so this is especially for our bipolar production partners interesting to build up their own cell with their own bipolar plate. And then they can investigate how good is the performance of their bipolar plate design in a fuel cell or an electrolyzer.
Okay, basically, so as you're thinking, maybe I should make my channels this way or something like that. Okay, or could you, maybe easy question, but could an air bubble also cause this?
Yes, of course.
Gas bubble.
Air bubble, or in an electrolyzer, you have, when you produce oxygen and hydrogen, you have also gas bubble production. And when you have too much of this gas bubbles inside the channels of the bipolar plate, then it could happen that it blocks, for example, the water flow. The thermal behavior is different. That means you can have thermal hotspots inside some parts of the cell. And this you can see with this device, and you should avoid this.
Okay, all right, understood. Okay. What do we have here?
Here you can see fluting effects. Maybe a little bit complicated scheme. You can see here the entrance of the cell and here the outlet of the cell.
Okay, so flooding means now the electrolyzer is filling with water, or there's the fluid where there's supposed to be a gas.
The fluting effect here is shown for a fuel cell.
Fuel, okay.
But it's the opposite effect. That means normally in a fuel cell, you want to bring the gases, hydrogen and oxygen, and the fuel cell produces also water. And when you have too much water,
yes,
then the gas cannot came to our crumb cake.
Okay,
Yeah.
So yes. So and what are we seeing now? Then this is over time again.
Yeah. The black line shows here the current production over the length of my bipolar plate.
Yes.
At the normal point.
Yes.
And then you can see within 60 seconds on the entrance the current goes from 440 milliamps to over 600 milliamps.
Right.
Yeah. 30% more. And the outlet it goes really down. Yeah. And this reason is that in the first area of your flow field we have the hydrogen and the oxygen, but here at the end we have too much water.
Okay.
And the water blocks.
Right. So the cell is trying to compensate
Yeah.
performance by going up
Yeah.
on this, and then there's more strain on the cells
Yes.
which are on the one side.
Yeah, and
Okay.
this you should avoid. But sometimes you will not see it when you have only your cell voltage measurement that you measure from the outside.
Understood.
Yeah, and when you have this tool, then you can see this and you can avoid in the future these situations.
Okay.
And this, and this effects always have an impact on the degradation of your cell.
Okay. And yeah, so how is this then set up in the lab when you set it up? I mean, obviously you're not putting on a vehicle, but yeah, can you show us a bit of that?
Yes, normally the customers use this to integrate it in their stacks. Yeah, but we have also a test system. You can see here on the slide where we also have the possibility to integrate then the membrane.
So this is the zoom in here. So
Yeah.
this is where.
Yeah,
your
this is
system
the test cell.
Yes.
And in this test cell we can integrate then our device, and the customer can integrate here the bipolar plate, the sealing, or the membranes
Okay.
on the electrodes, and then this a system that you can run then instantly. Yeah, and then you can make your own measurements, so
Yes,
you don't
yes.
need to build up your own test environment.
Yes. Okay.
This is also what we.
So this can come in a rack set up like this.
Yeah, you can see it also on the next slide.
That's
closer.
already zoom in. Yeah, okay.
Yeah, and then you can test your own equipment, cell equipment,
Yeah.
and then you can make 24/7 measurements. Yeah, and here also closer look to our sensor board. That is here integrated in the cell.
Okay.
The cell frame is here closed. And this is an electrolyzer cell, and then you can connect here our data acquisition system.
Okay.
And measure the system.
And I know you actually brought your, and I see if I can get it across here.
Yeah.
You brought your software with, so we can actually see how that looks live as you're running a system.
Yes.
So,
yeah, when you have integrate the sensor layer into your cell and to run your system, you can use the software to visualize then your system or your membrane. Yeah, and here, for example, you can see the current density distribution over. You can rotate this also to see it in the best way. And here in the middle, you have the temperature distribution.
Yeah, I mean, so when you look at it from the side, it's almost like the other diagram that we saw.
Yeah.
And now you have and these are the different channels.
This is a projection here.
Yes.
Yeah, and then we have here below some statistical values. That you can use this information to compare the situation of your cell. And finally, you can use then this information to obtain the parameter settings of your cell. And when you make 24/7 long-time measurements, then you will see after certain times, depending on the cell quality, that you have then degradation. That some parts of your membrane will not produce any more electricity or hydrogen.
So just to make it clear again, when I'm looking at this thing, when do I know that my cells have degraded or aged to a degree which I don't want? That means like when the one side is always down.
Often it's so that the profile is nearly equal. We have not so many changes.
Right.
You can change it a little bit by temperature, pressure, and other parameters. But then sometimes it will happen that the area where you have the most current production, that this part goes down.
All right.
And when you have this situation, then you should take a closer look, because then it could happen that you have irreversible effects of your cell.
Yes.
And then you are in the time of that your cell have higher aging, and that is more happening.
Okay. So there could be maybe a hole or something had really formed there. That's okay. So basically, what you're doing with these is you are allowing an inside view into the stack with these systems.
Yes. Yeah. Our customers use this then to improve the performance, the operating parameters.
Yes.
Yeah. Or they compare different materials, for example. They have maybe different bipolar plate versions that they want to test in the beginning on a single cell, for example, and then they find the best set of their cell, and then they build a short stack, for example, 4 or 5 cells, then test this again, and then finally the full stack.
Okay. So that means that you can actually, this is obviously fitting to one design, but you could actually reuse this if you had the same design.
Yes. This is normally customized because each cell has a different design.
Yes. Okay.
Yeah, and so we must design it for every customer new.
Okay, but then these other units are standard.
Yeah, the data acquisition system is the same.
Okay.
Yeah. And then,
so talking of standardization and same cell types and so on, can you give us a little bit of an outlook? Like what trends are you seeing? How are things going in this whole measuring area? We get a lot of feedback from our customers. Yes.
Can you measure this? Can you measure this? That we're seeing. We see also that, especially in the electrolyzer field, that they are spend a lot of time in testing currently. So we are currently more in the measuring time because they must understand the cells more before they developing the next
generation
for the big megawatt stacks. This is what we're seeing. We have also ideas.
So that means you're seeing bigger cells coming through.
Also bigger cells. We have also now the biggest cell with 10,000 square centimeter active area, so 1 meter to 1 meter.
Okay, so and you could make a measuring device that big.
Yes, we developed this also this
year. And would the cells, the individual cells be then bigger, or you could make this resolution as well?
The resolution could be the same, but when you have 10,000 square centimeter, then you have a lot of segments. But also for this customer, we have several thousand of the segments. And the customers want also, for example, to measure the impedance. Here we measure the current and the temperature. Here we have also a project that we can also measure then the distributed electrochemical impedance of the system. This a special topic. It's not so easy to understand, but when you make this technology or use this technology, you have also more information at which point happens the degradation on the membrane or on the bipolar plate.
Okay. Wow. Okay. Super interesting. So that means bigger cells, more impedance measurements, even more stuff to measure. And I think if you are working to increase the efficiency of these overall systems, and that could even let me say pay itself by increasing efficiency, leading to more output, that overall can help the hydrogen economy.
And finally, the investors want also safety. They want to know, can the cell really work 40 or 80,000 hours? And for this, our customers need measurement technology to monitor the cells.
And that's what you did. Maik, thank you so much for taking us through the whole aging process. And I hope that you can help the cells age less. Less degradation. Well, thank you for spending your time. Aging is the most valuable thing we have. Thank you for watching this video. It's been an absolute pleasure, Maik, for having you here.
Thank you very much.
If you want to get in contact with Maik and other people of the hydrogen economy, go on hyfindr.com, where you'll find wonderful products like this. All these things designed to make the hydrogen economy go forward. Please also follow our channel. There's many more videos to watch all around this. And thank you. Wish you success. Have a wonderful day.
Bye.
Thank you, Maik.
Thank you also.